triangles of degree distribution, which are fairly easy to model and fiddle with, but we would try to compute something that is very global and depend on the linking structure of the graph, like easy candidate is the distance distribution. So how many nodes are exactly at distance t? And another thing we are interested in is to try to understand which nodes are important in some sense, which is, of course, a very general and unspecified problem. Hi, David. So I'll try to be more precise. So first of all, this is really for real. So you can, if you're interested in doing this measurement, you can download the software implementing the algorithm I'm talking about as part of the web graph framework. And actually, they have been implemented in other large-scale streaming and non-streaming or shared memory framework, which I'm very happy with. And actually, we were able to run this on the whole Facebook graph using just a simple workstation, which was very nice. And this is the press, actually, that Michael was talking about. We ended up in the New York Times. But just by the New York Times got it wrong by enough by one. This is not the degrees, this is the distance. So the paper is 4 degrees of separation, and no, we are not crazy. We do not approximate 474 to 4. The degrees are 374. So the paper is 4 degrees of separation. Okay, just to, oh, you crazy Italian guy, they approximate 474 with. Okay, so our first motivation, as I said, is that we judge the goodness of models for networks using local first-order statistics. And, well, we have now knowledge to generate more or less everything like we want, like degree distribution, assortativity, and so on. So we will try to get something a little bit more global, like the distance distribution of the harmonic diameter, which is the harmonic mean of all distances, including infinite, which is very important when you measure stuff like the web, in which a lot of nodes are actually a pair of nodes are actually unreachable. Because the idea is that if you know something about like this about a network, it will be somehow, not maybe more informative is too much. It will give you a very different source of information about the network than, say, the degree distribution. Okay, because this really depends on how the network is interconnected and not really just on local properties. Now, one thing we are also, our first motivation was actually that one global property people use is the diameter or the average distance or something like that. But that's very difficult to judge, because then you say something like, you know, social network have logarithmic diameter. Logarithmic means that there is a big O, means that there is a constant, means that when you have a data set and you get 33, what does it mean? 33 is 33. I mean, if we don't have constants, we cannot judge anything. So we tried to fiddle with some more statistics, and the idea was, okay, let's look at the dispersion of the distribution, the variance to mean ratio of the distance distribution of graphs, and okay, this is a standard somehow terms, under one is under dispersed, over one is over dispersed, and the idea is that web graphs and social networks are very different with these aspects. These are web graphs of various size, from 100,000 to a few billion nodes. This is Facebook. And these are very social networks like Orkut or Hollywood and so on. So there is clearly a difference in the distance distribution. Okay? As we go on, we measure more networks, and we don't know why theoretically it happens. I mean, it would be very nice to have two different models for web graphs and for social networks in which we can prove that the distance distribution has this different dispersion property, but I don't know of presently of any model that does that. A second motivation to do this is geometric centralities. So geometric centralities are those centralities that depend on the distances on the graph, not on spectral theory like PageRank or dominant eigenvector, not on the whole set of shortest paths like betweenness centrality, but just on the distances. And these are actually the oldest ever defined centralities of this kind. You might be familiar with Bavela's closeness, 48. So basically the idea is that you take the sum of the distances to you, if this is large or peripheral, because there are a lot of nodes that are far from you, and then you take the reciprocal to have centrality growing with your peripherality decreasing. I mean, anti-monotone. Okay? This has obviously a number of problems if there are disconnected pairs. So if there are nodes such that dyx is infinity. So what people do is to omit those nodes, but the result is that the small components are really advantage. So what we're really interested in is harmonic centrality, which is a very small change, but actually is like game changer change, in the sense that now you can put infinity here. You get zeros in the sum. And this works on any network. I mean, these very good results on the web or in general network that have disconnected arcs. So we would like to estimate this on very large networks. And of course, we don't want to do n breadth first visits to do this, because that would be very difficult, like on Facebook. Notice that mathematically, this is like the reciprocal of a denormalized average. And this is the reciprocal of a denormalized harmonic mean. So from here to here, we're just moving from the arithmetic mean to the harmonic mean, which is a general trend in this network, starting with Marchiori and Latora's paper in 2000, Harmony in the Small World, which suggested that in general, when you have disconnected pairs, it's better to move from average of maxima or maxima to harmonic means. Okay, this is our second motivation. I'll try just now to treat you a little bit with, so this is the first 8 nodes of the Hollywood co-citation network by PageRank. Okay, this is a very famous porn actor, in case you don't know. And so we are not so satisfied with these results, as you can easily imagine, because there are a number of people we would not like to be in. If you take Betweenness, yeah, probably also here there are quite a number of results we are not so happy with. Harmonic centrality gives definitely a more realistic picture of what's in Hollywood now. So this is very anecdotal. If you're interested, there are a bunch of more mathematical evaluation of these indices that tells you that harmonic actually give you a very good signal, but this is just a trick. I mean, we really like to compute harmonic centrality on very large graphs. Okay, so what we do, how do you do this? Okay, there is an intermediate step in which actually what we do is we compute for each node of the graph. We compute in sequence the number of nodes at distance exactly t. Okay, and I will briefly explain how we do it, because this is the part that we cannot really explain well. So, for instance, if you add up over all nodes for each t, you get the numerosity of nodes of distance t, which modulo normalization gives you the distance distribution. So, if you can know this for each t in sequence, you can print the distance distribution. Nice. But you can also do other things like centralities, because the formula I've shown you can be easily rewritten in a different way. So this is just harmonic centrality, but instead of adding the reciprocal of the distances, I count the number of distance t and multiply this by 1 over t. This is just a different way of writing up that sum. Okay? Means that I count 1, the node at distance 1, then I weight 1/2 the nodes at distance 2, and then 1/3 the nodes at distance 3, and so on. But the nice thing of this is that I just have to know this number in sequence for every t and accumulate the result. So if I can enumerate for each node the number of nodes at distance t to x, it's very easy by keeping track with a single floating point per node of this summation. And in the end, you will get harmonic centrality. So these are the two things we are really interested in, distributions and harmonic centrality. Okay, how do you do this? The basic idea is comes from a paper that has now 11 years. Actually, it appeared in some previous paper, but in a very hidden form. So the idea is to use dynamic programming. So let Tx be the ball radius t around x. So distance at nodes at most t from x. Note that when talking about centrality, we want the incoming path. So you will have to apply all this to the transpose graph. I won't say any more about this in what follows. So clearly the ball radius 0 is just x, but the nice thing is that you can compute any ball just by dynamic programming if you know the smaller balls. So the nodes that are within distance t plus 1 from x are x, and the nodes at distance at most t from each of its out neighbors. Okay, because if I can go from x to y in t plus 1 steps, I must have done one step to get to a neighbor, and then at most t steps. So we can just start from this and iteratively compute this, which is very nice for a number of reasons. First of all, this computation is very highly parallelizable because it's independent for each b3 plus 1. Second, it can be done just by enumerating the edges x, y in lexicographical order. So it's almost streaming on disk. You don't really need to keep the graph in memory. So there are a number of ways why this works very, very well. The obvious, okay, once we have this in sequence, we can just take these differences, and these will be our nodes at distance t. So We want to compute balls because we want to know the size of the balls, because we want to take differences, because this will give us the number of nodes at distance t, and from the node at distance t, we can do distance distributions, we can do harmonic centrality, and also a lot of other things. Now, the somehow obvious problem is that this is very expensive because each set uses linear space. It will be quadratic in the size of the network. So we cannot really do it. So what we do is actually we use approximate set with some objects called probabilistic counters, which are so rough, such rough representation of a set, that actually the only answer they can give you somehow reliably is the size of the set, nothing more. You cannot really ask which elements are in the set. And they are very, very small. But the main point is that we need such an approach. Okay, this is not really English. We need an approximation of this kind from which we can compute unions quickly. So we will never keep an explicit representation of these balls. We will just have this very small log n bit probabilistic counters that will be combined doing unions. And okay, now this will be so statistically rough that someone will probably have some problem at the stomach, but it's just a slide that tries to give the idea. So the idea of these counters, which were developed by Flageolet and his school, and are widely used in the industry, you can find papers about that from Google or from Aggregate Knowledge and so on, is just that instead of, we see a stream of elements one by one, but instead of keeping track of the set, we keep track of a very simple feature of the set. And the feature is computed in this way. We take the number of trailing zero of a very good function, hash function applied to each element of the set, and we take the maximum. So the idea is that if you see very few elements, your hash function will give you mostly odd values, and you get 0. But if you start to see many elements, you will start to see something that is divisible by 4, by 8, and this maximum will rise. Okay, essentially what you do is to keep the track maximum of the m, and you can show that essentially log n bits, okay, great, are sufficient. And okay, this is very bad because this process doesn't even have a finite expected value. But basically, what you get is that the number of distinct elements you've seen are 2 to the power of m. There are a very huge number of things you can do to make this work, like to have multiple counters to decrease variance. You must use harmonic mean. I mean, there is a very nice paper by Flageolet, 2 or 3 papers by Flageolet about this. But the nice thing of this process is that the counter associated to a stream, a combined stream, is just the maximum of the 2 counters. So if I see a stream A, a stream B, I get 2 numbers, 5 and 7. What would be the number associated to A and B in sequence? The maximum of 5 and 7. So it's very, very easy to compute union in this very approximate representation. It's just the maximum. So what we do is actually keeping in memory track of the ball of radius t uses this very, very simple sketch. Okay? And then we go on computing maxima, basically, which will give us the ball of larger radius. And okay, this is an example of how convergence works. So depending on how much memory you use, this counter has a guaranteed relative standard deviation or relative coefficient of variation, however you want to call it. And depending on how, this is the standard error curve, how many trials you do taking average, this is improved. So this is the theoretical precision, relative precision of each counter. Okay? Now, I've told you that we do a number of things. We take differences, we divide by t, blah, blah. Then we gather up, and these are the statistics of the actual error computed on a small graph so we could have exact values of harmonic centrality. So you see that practically what happens is that harmonic centrality converges even better than the theory would say of each single counter. So this is the average relative error, the usual box plot. I mean, quartile, average, plus minus standard deviation. So what happens is that we have these counters. We have a theoretical guarantee of precision. Actually, we get something better when we aggregate the data. But now the point is that this is nice, but it shouldn't really happen. So it shouldn't really happen because we're taking differences, and we have a relative standard error guarantee. So when we are, say, at the end of the computation, and a ball is 1 billion nodes, and the next node is 1 billion plus 1 nodes, we are estimating 1. the difference between the two balls. But we have two estimators for the 1 billion node and the 1 billion plus 1 ball that are 10% wrong. And when you take differences, there is no way to guarantee that these two errors combine well. So your error is about order 1 million, and you're estimating 1. It shouldn't work in theory, but when you try to check against the ground truth, actually works, and everybody is doing this, just to say I'm not the crazy guy. I mean, everybody is actually doing this. But the basic problem here is that you cannot take the difference of two estimators with a bounded RSD and get an estimator with a bounded RSD. You can get the sum of two positive estimators with a bounded RSD and get the same RSD, but you cannot take the differences. Nonetheless, we observe a very good convergence of every small network for which we can actually have different exhaustive mean of computation. Like the graph I've shown you is on Wikipedia, is 5 million nodes, is like 1 week of parallel computation on a nice workstation. You can get exact harmonic centrality. Or if you have a billion node MPI cluster, probably you can do better, but we don't have it. This might be related to the fact that there is some very deep interconnection between the balls. I mean, there is the graph structure in between. I mean, these balls are not completely random pieces of information. They're extremely dependent. So on one side, the dependency makes it difficult to do statistical analysis. On the other hand, we know a lot how this ball evolved during the computation. Okay, and so maybe it's just a general statistical phenomenon. You aggregate a lot of data that have error in all directions, and then you get something better. First of all, I want to make very clear that I'm an algorithm guy. I have very little feeling for statistics. I mean, my gut feeling for statistics is usually wrong. So I'm very interested in getting people interested in this problem because I will never publish a paper about that. But I would like to know why what we're doing actually appears to work. Okay, there is an easy observation you can do based on the graph structure. There is a three-phase evolution of the computation. So basically what happens is that so at the start, you have the graph, and the balls are very small, okay, radius 1 or 2. These balls basically are independent estimators because there is no intersection. So from the point of view of the estimator, you're just reducing, not increasing the RSD because you have 1 billion completely independent estimators. So the fact that on the very first phases of the computation everything works is not so weird because we're somehow exploiting the fact that until these balls get to the point where they start to intersect significantly, basically we are just doing independent estimation. So at some point, balls start to intersect. So we start to get dependency. But what happens is that, at least for the distance distribution, but the phenomenon transfers to, then we are in the peak of the distribution. Now, for the network study, the peak of the distribution is of the order 0.1, 0.2. I mean, it's a lot of probability mass. And the error we get, the relative error we get, is like 1%, sorry. So if we have 1% relative error, translate to 1 over 100 absolute error when you take differences, not bad. I mean, yeah, okay, here we don't really know what's happening, it's a mess, but the error we get, the absolute error we get is good. Okay? So I explained you why, just with some hand waving, I believe this part works. And then there is the tail. The tail is very interesting because something happens, everything becomes totally dependent. I mean, when we are in the tail here, let me do it with the CDF because it's clear. So we are doing something like this, okay? In the very last phases, this ball change very little. So they are almost identical one another. So the error is all on one side because the error depends on the actual set that is in the counter. And when we are just in the final part, you know, like I'm getting this and just a little bit more at each step, the elements I've seen put in the set move the arrow completely towards a single direction, like minus 10%. And all the successive values we get empirically have exactly the same error. So when you take two estimators that have exactly the same error in practice, well, this relative error transfers to the difference. And this is why, even if it's completely crazy, we get extremely precise estimations here. But again, it's completely crazy because we have, our absolute error is 1 million and we're estimating 1. Okay? So this is the best I can say about why I believe this is actually working so well. But it would be very nice to have either some combined statistical graph theory explanation of this, or some general statistical analysis of the phenomenon. Notice that we actually, just one thing I finished, one thing, when we have examples of networks in which the distribution is not so peaked, which is like something like that, like road networks. And here is where really we see from real exact computation to approximate computation a big mistake. I mean, we see the actual absolute error coming in, and you get something like this instead of what you want. So it appears that at least the middle phase can be wrong as much as the absolute error. The other two does not seem to be so wrong, but maybe because of this phenomenon. I'm over. So.
Well, there's a question that are related to graph structure. Have you tried to apply this to Erdős-Renyi graphs or?
Or Erdős-Renyi graph, if they are enough, they have diameter 2, so it's not very. I mean, in 2 runs we are over.
Yeah, so.
Yeah. We try to. Well, we run this, of course, to check whether the speed was correct, like in an approximate, in a preferential attachment model, or Erdős-Renyi model. We tried to run this on large graphs, but the problem is that everything converges like in 3 steps. So if you try even worse Kronecker graphs or stuff like that, it's 2 steps. So it's absolutely unrealistic, and it's very difficult to get any. Otherwise, you must put down the coin toss of the Erdős-Renyi model so low that you get a very disconnected graph, and again, you don't get much information because there is no dependence at that point. So it's even very difficult to tune the parameters of the. But yeah, I mean, what we tried to do was to have an algebra of graphs in which, if you know explicitly the CDF of the 2 pieces, you can compute directly the CDF of the combination. You can do it for very simple graph operation like Kronecker product, but then it becomes completely impossible once you start to overlap. Because in this way, we would have had the possibility of having explicitly the CDF of very large graphs, which very rarely is known. But then we got against some wall and we stopped, basically. Thank you.